Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 7, almost finished. One section to go after this. So today we're talking about Section 7.6, which is proportion and problem solving with rational expressions. So we're going to look at a variety of applications in this section. We're going to start with proportions, using proportions to solve problems, solving problems about numbers, what I affectionately call who cares problems, problems about work, shared work, and problems about distance. And we're actually working on a different SLO in this section. Anytime we do applications, we're actually working on SLOE, which is solve application problems using methods covered and available technology. So for us, that generally means a calculator. All right, so what is a proportion? A proportion is an equation that states that two ratios or fractions are equal. So I have an example written down here. So what we're going to do now is switch over to the tablet. I'll show you how we would have solved this problem in the last section, and then we will look at a shortcut. All right, so the way that we would have dealt with this equation in the last section is we would have found the LCD, which is 3 times x plus 2. And then we would have multiplied both sides by that LCD because this is an equation. And then, oops, come on. This thing is so tricky to write on sometimes. All right, so now I'm going to sneak my ones underneath those expressions. On the left-hand side, I can get rid of the x plus 2, and on the right-hand side, I can get rid of the 3. And what I end up with is 3 times x plus 1 equals 5 times x plus 2. All right, now if I, let's see, this isn't going to look super pretty. I'm trying to get as close as I can to my original equation back. So pretend that those two denominators are not crossed out. All right, what I want to point out to you is that I could have solved this equation just by doing this. Multiply those two together and multiply these two together, right? So that is a shortcut that's called cross multiplying. For many, many years, I used to be very nervous about showing this shortcut because students had a tendency to want to do this anytime two fractions were in the same zip code. You only do this when it's a proportion, when it's one fraction equals one fraction. You don't do it when you're adding fractions, multiplying fractions. This is the only time you use this. All right, so if you promise me this is the only time you're going to do this, then you can go ahead and use this. All right, and now, of course, it's very easy. This is just a linear equation. We're going to distribute the 3 and distribute the 5, and that's going to give us 3x plus 3 equals 5x plus 10. And because it's a linear equation, we're going to put all of our x's on one side, let's say the left side. And we're going to put all of our numbers on the other side. And that's going to give us negative 2x equals 7, which means, I guess we should call it the possible solution of this equation is x equals negative 7/2. Remember, we talked about in the last section when you're solving a rational equation, you do need to make sure that none of your possible solutions makes a denominator 0. The only number that would cause me a problem with this equation is negative 2. Notice the x plus 2 there. And so since this is not a negative 2, this is a perfectly good solution. Remember, we wrote okay to indicate that we did look at those original denominators. All right, so here's the official rule. If A over B equals C over D, which is the form of a proportion, then that means that A times D is equal to B times C. Remember, all you do is just, let's use this. Multiply these two together and multiply these two together. All right. Let's see what we have next. Okay, so here are some examples of using proportions to solve problems. I've got these all written out on the tablet. First, we have what I call the Martian problem. I didn't create that meme. There was actually one floating out there that was captioned the Martian problem. All right, and then a similar triangle problem. That is a classic application of proportions. And then finally, we have a problem about numbers. So the reason I call this a who cares problem is because you read it, 12 divided by the sum of a number and 2 equals the quotient of 4 and the difference in the number and 2. So usually when I do a word problem, I'm actually really curious what the answer comes out to. They haven't put this one in any kind of interesting context, so I'm really not curious what the answer is. But it's still worth doing because this is a good kind of problem to warm up on, to be able to do more interesting types of problems. All right, so let's go back to the tablet. All right, starting with the Martian problem. If a 170-pound person weighs approximately 65 pounds on Mars, about how much does a 9,000-pound satellite weigh? And then they want us to round our answer to the nearest pound. So let me get my calculator ready. All right. So proportions are actually pretty easy to set up. Oh, I've never told you before about Mitchell's commandments, have I? All right. Yeah, this can work in an online class. So I know that word problems freak out a lot of people. So years and years ago, I came up with what I call Mitchell's commandments. There are only 2 of them. Mitchell's first commandment says, thou shalt clearly define a variable. All right, so whatever they're asking you for, 9 times out of 10, you're going to name your variable after that. So in this case, why don't we say let x equal weight of satellite on Mars. Okay, and then your proportion could go something like this. 170 pounds on Earth, that letter E stands for Earth, is to 65 pounds on Mars as 9,000 pounds on Earth is to X pounds on Mars. There are a few different ways that you could set up this proportion. What I recommend is have one set of units on top and have another set of units on the bottom. Often you will have 2 different sets of units in your proportion problem, not always. Okay. All right, so again, the way I read that is 170 pounds on Earth is to 65 pounds on Mars, as 9,000 pounds on Earth is to X pounds on Mars. And then once you're convinced that you've got it set up correctly, you can drop all your units and just say 170 over 65 equals 9,000 over X. And then remember the shortcut we talked about. Multiply these 2 together, multiply these 2 together, and that gives you 170x equals 65 times 9,000. And I'm not going to bother figuring out what is 65 times 9,000 because what we really want to know is what is the value of x. So we're going to divide both sides by 170. And what I really want to know is what is the value of x. So what I really want to know is what is 65 times 9,000 divided by 170. And as many times as I've done this problem, I'm a little surprised I don't have the answer memorized. Okay, and then remember they wanted us to round it to the nearest pound. So my calculator says 3,441.17647. I'm just going to round that to 3,441 pounds. All right, and then I was talking about Mitchell's commandment. So Mitchell's first commandment is thou shalt clearly define a variable. Mitchell's second commandment is thou shalt write thine answer as a complete sentence. So you could say something like the satellite would weigh, or let's just say weighs about 3,441 pounds on Mars. So there are a few different reasons I like you to write a complete sentence for your answer to your word problem. And of course, if you're using an online homework program, it's not going to have you do that. It will probably have the sentence all built up already, and then you just have to fill in the blank where the number goes. So try to get in the habit of doing this on your written work. I promise you more partial credit if I check that problem. If you've followed Mitchell's two commandments than if you don't. Another reason I like you to write a complete sentence, I always think of this one student I had years and years ago. This was near the beginning of my career. I was teaching a pre-calculus class, and we learned this method for finding the distance between two cities. And so one day we had a quiz, and the question was, what is the distance from Dallas to Omaha? And somebody came up with the answer 5 million miles, which is totally understandable if you make a certain kind of mistake with the formula. I like to think that if this person had written the distance from Dallas to Omaha is 5 million miles, that maybe they would have realized something's wrong. All right. So that's the other reason I like you to write your answer as a complete sentence, that you'll catch those, sort of goofy answers that don't make any sense. All right, so let's go to the next example. This is letter B. They want us to find the unknown length y in the pair of similar triangles, which I have tried to draw for you there. Okay, so again, a couple different ways you could set this up. I think the way that I'll do it is to say, okay, so what kinds of triangles are these? They look like they might be isosceles. Isosceles triangles have two equal sides. So typically what I like to do with these is put corresponding parts of triangles in the same ratio. So for example, you could say 12 is to 5 as 10 is to y. All right, that's one way to do it. It's not the only way. You could have also done 12 is to 10 as 5 is to y. That works. Okay. All right, so once again, we'll cross multiply. And that is going to give me 12y equals 5 times 10, which I know is 50. And then I divide both sides by 12. And I get y equals 50 over 12. Okay, now at the very least, I need to simplify that fraction. 50 over 12 is not simplified because both of those numbers are even, right? Okay, so if you pull a 2 out of the top and the bottom, you get 25 over 6, as in 25 over 6 meters. I think that's a funny sounding answer. If you go into Lowe's and ask for 25/6 meters of anything, you know, boards or carpet or whatever, they're going to look at you weird. I would recommend either changing that to a decimal, or I believe what your online homework is going to ask for that is a mixed number. So just in case you forgot how to convert improper fractions into mixed numbers, it's just long division. You do 6 into 25 goes 4 times with 1 left over, which means 4 1/6 meters. So I didn't do Mitchell's first commandment in this problem because the y was already there. I guess I will write my complete sentence. The unknown length is 4 1/6 meters. I guess I shouldn't call it an unknown length anymore now that we know it. Oh well, you know what I mean. All right, last example from this group is the who cares problem. 12 divided by the sum of a number and 2 equals the quotient of 4 and the difference, oops, I have a typo there, the difference of the number and 2. Okay. All right, so for a who cares problem, you can just say let x equal the number. By the way, Mitchell's commandments are only for word problems. I have seen students get carried away and try to do this in every single problem. Only word problems, all right? Okay, so let's try to translate these words into math symbols. 12 divided by the sum of a number and 2. So I'm sure you know that sum means add, right? So if you're dividing 12 by the sum of a number and 2, that's going to look like this. Equals the quotient. All right, quotient also means divide, so they were trying to vary up their language there a little bit. One time they said divided by, and another time they said quotient. The quotient of 4 and the difference of a number and 2, the same number. Difference means subtract, right? All right, so there's our proportion. Once again, we will cross multiply, which gives us 12 times x minus 2 equals 4 times x plus 2. And this is a lot like that very first example we did. You should pause the video and try to finish this one off. All right, when you come back, I'm going to do it really fast, okay? Okay, so I'm going to take your word for it that you paused the video and tried that. 12x minus 24 equals 4x plus 8. Let's put the x's on the left side. Let's put the numbers on the right side. And that gives us 8x equals 32, which means x equals 4. So in a who cares problem, your sentence with your answer is very short. It can just say the number is 4. All right, so hopefully that doesn't seem too bad. Let's go back and see what else we've got. So disappointing. I went to set this up today and I thought that my tablet was going to work the way it had been up until the end of last week. I tried it. It doesn't work that way. I still have to do it this sort of clunky way. Okay, shared work problems. These are a lot of fun. All right, now I got tired of typing out the whole entire problem on the tablet, so I just summarized it. So let's look at this first one. It says, Mr. Dodson can paint his house by himself in 4 days. His son needs an additional day to complete the job if he works by himself. So the question is, if they work together, how long does it take to paint the house? Okay. And while we're here, let's read these other problems because, again, I've just got them summarized on the tablet. The next one is very similar. It says, Mrs. Smith balances the company books in 8 hours. It takes her assistant 12 hours to do the same job. If they work together, find how long it takes them to balance the books. So again, very similar to letter A. And then I want you to think at some point about letter C. Is letter C like letter A and letter B? One person proofreads a copy for a small newspaper in 4 hours. If a second proofreader is also employed, the job can be done in 2.5 hours. How long does it take the second proofreader to do the same job alone? All right, so let's go over to the tablet. Okay, here we go. So letter A, this was the one about Mr. Dodson and his son painting the house. All right, I remember the very first time I ever taught this kind of problem. I really liked the way that the book I was using explained it. They started by talking about some wrong ways to do the problem. So the first wrong way would be to say, okay, well, it takes Mr. Dodson 4 hours. It takes the son 4 days, sorry. It takes Mr. Dodson 4 days. It takes the son 5 days. Therefore, it takes Mr. Dodson plus his son 4 plus 5 days. It takes them 9 days. So I hope you're laughing because that doesn't make any sense at all, right? If Mr. Dodson can do the job himself in 4 days, how could it possibly take longer if he has help? All right, so let's get rid of that. Another idea that maybe makes just a little bit more sense, but still can't be right, would be to like take the average of 4 and 5. Does it take 4.5 days? No, again, that's longer than 4 days. So it has to be less than 4 days. All right, so here's the idea. And actually, once we figure out how to set these up, it's really easy to do any of these. So let's look at what it looks like after 1 day. After 1 day. All right, so here is my house that I've probably drawn the same way since I was 5 years old. All right, so after 1 day, Mr. Dodson has painted 1/4 of the house, so about that much. And after 1 day, the son has painted 1/5 of the house. And hopefully he's not painting it a different color. I guess that would be one reason it might take them 9 days if they work together. Right? No, they're painting it the same color. Okay. All right. So again, after 1 day, Mr. Dodson has done 1/4 of the house. The son has done 1/5 of the house. Together, they have done 1/4 plus 1/5. And by the way, you really don't have to write down this part. I'm just trying to sell you on the way that we're going to do this. Okay. So how do you add 1/4 plus 1/5? Hopefully you can almost do that in your sleep. You get your common denominator, which is 20. Multiply that 5/5, multiply that 4/4, and that gives you 5/20 plus 4/20, which is 9/20. They get 9/20ths of the house painted. All right. Okay, so we're going to call the answer X. All right, so we saw that after 1 day, they get that much of it painted. After X days, Mr. Dodson, let's see, how do I want to say this? Oh, we'll say it like this. Mr. I used to explain this the same way every time for a long time. And then just within the last few years, I started explaining it differently. So let me do this. Let's just get rid of all this. Okay, I know how we're going to do this. All right. We're going to make a little chart. So on one side of the chart, I'm going to say time. Let me move this up a little bit, give myself some more room. Time to do job. And then over here, I'm going to say part done in 1 day. Okay, and then over here, I'm going to put Dotson, son, and then together. All right, so it takes Mr. Dodson 4 days, which means the part he gets done in 1 day is 1/4. Takes the son 5 days, so the part he gets done in 1 day is 1/5. All right, so now I'm going to define my variable. I'm going to say, just call that X days. If you wrote something like this in your written work, I would count that as Mitchell's first commandment. So together it takes them X days, which means the part that would get done in 1 day is 1/X. All right, dun, 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 dun. So our equation that we're going to solve to figure out how long it takes them to do the job together is the part done by Mr. Dodson in 1 day plus the part done by the son in 1 day should equal the part they get done working together, right? So this is how I recommend you set up every single one of these shared work problems, okay? All right, so now I need to make some space to solve this equation. I should have left a blank. You know what? Hold on. I'll just skip to the end here. No. Okay. Spoiler, spoiler. There we go. All right, so the equation is 1/4 plus 1/5 equals 1/X. This is the type of equation we solved in the last section. We need a common denominator. None of those factors have denominators have any factors in common, which means that you can just multiply those together. 4 times 5 times x is 20x. So if I multiply both sides by 20x, I'll do the easy side first. Over here, the x's cancel and just leave me 20. And then over here, I'm going to distribute my 20x onto the 1/4 and the 1/5. All right, so 4 goes into 20 5 times. 5 goes into 20 4 times. So that leaves me 5x plus 4x equals 20, which means 9x equals 20, which means that x is 20/9, aka 2 2/9 days. Okay. So here's how I'm going to try to sell you on that answer. Think about what happens after 2 days. after 2 days. Because remember, it takes Mr. Dotson 4 days. After 2 days, Mr. Dotson has done exactly half of the job. But the son is not finished with his half. Okay. So for that reason, it has to take a little bit more than 2 days. On the other hand, after 2.5 days, let's say that they've made a deal that, you know, each of them is going to do half, which, by the way, is not how this works. With shared work problems, there's always an assumption that they both keep working until the job is done, which means the faster person is going to do more of it. That's fine. If you're just trying to get it done as fast as possible, that's how you do it. But let's say that they agreed to each do half. It would take the son 2.5 days to do his half. And by then, Mr. Dotson, you know, he's already been done with his half for a half a day, and he's, you know, sitting on the lawn with a beer. All right. So it has to take somewhere between 2 and 2.5 days. So I would say this is a very reasonable answer. All right. 2.25 would be a good guess, and that's very close, but not exactly spot on. Okay. I'm going to skip doing Mitchell's second commandment on this problem, if that's okay with you.